9.
Oh, the ends.
9 is the stack.
So this is
No.
N1.
Water is 1.33.
I was
Right.
right.
Glass is 1.5.
Yeah, look at me.
We'll do 1.3.
So smart.
So N1 sine theta 1 equals N2 sine theta 2. So this is so important that you remember this. These angles are measured from that normalcy line, okay? It isn't measured from the horizontal, it's measured from the line that's forming a vertical angle or right angle to that surface. Okay. So I've got air, and unless you're technically, air does have an index of refraction because technically it's not a vacuum, but it's so small, just don't even worry about it. So unless I specifically tell you to use something else for air, just let the index of refraction of air be 1. Okay, it's not a vacuum. Let it go. Okay, just let it go. So this is going to be 50 degrees. So I'm going to shine that light in there at 50 degrees. So what I'm trying to figure out is that when that light goes through there, okay, is it going to go more shallow like this, or is it going to go more vertical like that? Okay? Or is it just going to stay the same?
More vertical.
So, remember, this angle that we're going to find is going to be relative to that 90-degree line. Okay? Relative to that 90-degree line. So here's the math. So we have N1, which is your air, times the sine of, in this case, 50 degrees. That's going to equal N2, 1.33 times the sine of theta 2. So how are you going to get that second angle?
Divide by 1.33.
You're going to divide by 1.33 and then take the inverse sine. Okay? So I'm going to take the sine of 50 times 1, divide that by 1.33. And then take the inverse sine of all of that. What do you get? What'd you get? So call it 35.2 degrees. Okay? Now, here's the question. Where is that 35.2 degrees? Is that 35.2 degrees out here? Or is the 35.2 degrees
Normal line.
Yeah, relative to that normal line. Okay? So that should make sense. So what happened is that as this light came in, hit the water, this side slowed down because it's more optically dense. It gets slowed down, it gets turned, and then it's going to go like this. Okay? So this is why this is 35.2. Okay? Now, what if we went into the more optically dense medium where the index of refraction was 2?
Oh, smaller angle.
Big change, what?
25.
Divided by a bigger number. Now we're going to dividing by 2.
Yep.
So what do you get for the angle now?
25 degrees.
22.52.
So if we make the index of refraction in the new medium 2, we make it more optically dense, there's going to be bigger difference in the speed and it's going to get bent more. So if you do the math on that one, if the new index of refraction is 2, what do you get theta to equal? What did you get?
22.5.
22.5 degrees. Okay? So what that means is that that first one, when you came in at 50 degrees, that shallowed out to 35.2. And that's where N was 1.33. But if you change it to where N is 2.00, then what happens?
Goes down to
Then it builds a lot more, and that angle becomes 22.5 degrees. Okay? So the bigger the difference there is between those two values, the more it's going to bend. Now, what if we did this? Here's water. Here's air. And I shine the beam of light at 30 degrees. And then it's 1.33. I want to find that angle. Okay? Cool. So, N1 is going to be 1.33 times the sine of 30 degrees is going to equal 1, because we're going into air, times the sine of theta. So what'd you get for theta? Well, what's the sine of 30? 0.5. What'd you get? 41.7 degrees.
Sure.
Okay? Now, 41.7 degrees. But remember, that's this angle here with that normal line. So that's going to be 41.7 degrees. Notice what happened to that line. What did it do?
Became more horizontal.
Then more horizontal. Okay? So, again, if you like that visual, it comes in, this side speeds up, the top side of that wheel speeds up faster because it's the first one to hit dry pavement. Boom, it gets bent, it speeds up. Okay? Here's the most critical thing, is that this, you have to remember, these angles have to be relative to that 90-degree line. Now, this is where this gets a little bit weird. Just a little bit. And this runs into what would happen if you are swimming in the water. Okay, so let me kind of redraw this whole thing. So here's the water, and you're down here
Gavin, try running in one.
swimming. Okay? You'll even give you flippers and a snorkel. Okay? And the sun light is coming in here. Okay? Now, if that sunlight comes in here and hits the water, what's it going to do when it hits the water?
It's going to go like,
Further.
It
It's
goes
going to go
straight
more
down,
down.
but not 100% straight down.
Something more like this.
Yeah, I like that.
Okay. Now, this is where this gets a little bit weird. Just a little bit.
No.
So if you're down here snorkeling and you're seeing that light, and this is going to be an important skill, it's like a theoretical thing that you need to be able to visualize. When you see that light coming in like this, you're going to think the sun is actually up there, because that's where that light looks like it's coming from. So your eye naturally wants to trace back in a straight line. So even though the sun is here, you're going to think it's further up on the horizon, because that's the path that it looks like it took. Okay?
So like if I go spear
I did
fishing,
immediately have a thought of like
I need to aim.
how optically dense would something need to be.
Well,
to think that it's
But it depends. If you're spearfishing and you're up here
Yeah.
looking in,
Oh yeah.
okay? So you're seeing, and we'll get into this, so you're seeing the fish down here.
Yeah, I need to aim.
So what has to happen for you, go back to this. For you to see the fish, what has to happen? The angle, the light has to bounce off the fish,
back in my.
go up. Now, as that goes up, what's it going to do when it goes from the water into the air? It's going to flatten out, right?
Yeah.
So,
you have to aim
for you, it's going to look like the fish is over here.
Yeah.
But you gotta
Okay.
get closer.
But the fish is going to look like it's here.
Yeah.
Where do you have to aim?
Ahead of it.
Oh,
You
now
have
I
to
know how
aim
to
in
do this.
front of it.
Survivor. I'm gonna
Okay.
try Survivor.
All right.
You should be in Survivor.
No, you eliminate that if you just look straight down.
You
Okay, but we'll get into depth later, because the depth isn't even the same. That gets wonky even with the depth. Okay. Oh, yeah.
Your family job.
Oh, yeah.
It's fine.
Oh my God.
This is easy.
Our
I
brains-
like this.
Our brains are growing.
I'm not insane yet.
Are they really?
Mr. Burke,
Yeah.
I think
I
you're
mean, we'll
forgetting
get
something.
to it.
What?
You said that we'd have an off day today.
Oh, I never have, no.
You said rest day.
Nice, yeah, like-
That's funny.
Good guys like Gavin, we really tried with that one.
Yesterday was rest day.
I have Stars Bowl today.
You got to say
I have to do
yesterday.
this thing I signed up for.
Got a test.
I
That's
might
day.
not have this all done.
I have to do the thing I signed up for.
Well,
I'll tell you now, number 6 is the hardest
Is
one.
that 9?
9 to 11.
Number 6.
Is that what's written?
What do you
Okay.
What page is this?
It's
594.
Hey, not all of us can find
Luis,
the last six squeaky
594.
I had Ken. Not all of us can find it. You actually did not have to do that. I had to.
And the index for the indexes of refraction is 538.
Page what?
538 for the index of refraction.
I don't know.
Page 538 are the indexes of refraction.
9 through 11.
We gotta go.
Where is that?
Yeah, May South people, you gotta go. Number 6 is a
Is that-
geometry
Is that
problem.
11 or 13?
Oh, I know what.
11.
9 to
Number
11?
six.
Why are you cheating?
I know.
So
My
basically
favorite.
what's happening on number 6, you're shining a light off of the wall, and then you have to hit a target that's not in the same depth.
I know my trick.
Let me give you a hint.
I can play pool now.
Look at tangents.
No.
When you get to number 6, use tangents.
This is not 9 to 11.
Huh?
Yes, 9 through 11.
Yeah, that's 9 through 11.
I'm very good at 9.
Um,
Yeah, that's 9 through 11.